Today, we're taking a look at 100 years since quantum mechanics first reshaped science. Quantum mechanics didn't just change science itself, but it changed our very view of reality. Uncertainty, probability, these things were no longer abstract concepts, but they were woven into the fabric of nature itself. Quantum mechanics wasn't just a philosophical shift, it was a technical shift as well. Without it, we wouldn't have semiconductors, MRI scanners, or even quantum computers that are being built today. Today, quantum mechanics is a vast industry, with hundreds of thousands of researchers across the world extending that legacy that was started 100 years ago. Here are 5 physicists exploring 100 years since the advent of quantum mechanics.
We are all quantum physicists. Almost every branch of physics underpinning that is quantum mechanics.
On one side, there is a fundamental understanding of reality, what reality even means. On a much more pragmatic level, our everyday life is really governed by those developments.
Before we had quantum mechanics, we didn't even know that there were questions we could ask within classical physics. They simply made absolutely no sense. Exactly 100 years ago, Heisenberg published a very mysterious paper. This transformed our understanding of microscopic physics. Prior to that, it was all Newtonian. But what transpired with Heisenberg was this idea that there are certain things you simply cannot access with a perfect accuracy.
You can measure the position of a particle with some precision. You can measure the momentum, the notion of motion or speed of a particle with a given precision, but you can never measure both with ultimate infinite precision. It was a complete shift of paradigm in the way we think about things. In 1926, Schrödinger came much more with the notion of wave. Already from Einstein, we understood that light, which is an electromagnetic wave, is fundamentally quantized. So the notion of waves was starting to have a very fundamental aspect in all of the description of quantum mechanics.
Schrödinger and Heisenberg had very, very different ways of looking at quantum mechanics. Schrödinger wrote down his famous equation, the Schrödinger equation. It was a way of extending classical physics to these new phenomena. Heisenberg, in some sense, was the more radical of the two, because he invented matrix mechanics, and that is much closer in spirit to the, say, modern quantum information theory.
Schrödinger already in 1927 had the feeling that quantum mechanics should be a universal theory. There shouldn't be a dichotomy between the microscopic and the macroscopic world.
You get pretty much the whole theory there, including this notion of entanglement, where you have these two particles that can be correlated in a way that no classical particles can be correlated. That comes at the very beginning with Schrödinger. And yet people didn't understand it until, decades later.
There was de Broglie saying we should return to classical physics. There are going to be really hidden variables. We can describe quantum mechanics the same way. It's not really uncertain. Then there was Copenhagen saying, not at all. There can't be like that. We need a classical context, and there are certain things we can never do simultaneously. They said when an electron goes from one orbital to another, it really jumps, almost like an instantaneous jump. Einstein didn't like that at all. And then there was Schrödinger saying, well, wait a second, I think there is a way of coherently describing the whole of universe quantum mechanically. And it's interesting that these 3 directions, if you like, still exist in our contemporary debates.
The debate that started actually almost right after the proposal of these laws was all about what they meant for physical reality. Of course, all interpretations agree on the experimental predictions, on what we see in the laboratory, but they differ greatly about what the ontology, right? So what's behind this stuff that we see, the clicks?
A very practical interpretation, just shut up and calculate interpretation, where you make a measurement, you get a probability given by the Born rule, and that's the end of it. There are these spontaneous collapse models. That is a belief that the collapse of the wave function is a physical process which occurs because there's this ad hoc field, this invisible field, which kind of hits your particle and causes it to localize and collapse. I think the one that is probably most compelling to the majority of physicists is called the many worlds interpretation. It's compelling because it says that fundamentally we are also in superposition.
Every possibility has a realization in different worlds, but because those different worlds are not connected with us, it's not that they're in different dimensions, it's not that they're in different realities, they're simply different outcomes. We're not connected in any ways with those, so we can never actually probe them and understand whether or not this interpretation is real. It's just a way to understand it for ourselves.
Cubism is the idea that the wave function is nothing more than a description of our knowledge of the physical world.
For a cubist, the thing where reality actually happens is when an agent takes an action on the world and the world reacts. So, and in quantum mechanics, that would mean that's the act of measurement. So reality happens whenever a quantum agent or an agent takes a quantum measurement.
In terms of the standard interpretations, they all have some compelling features, but they give the same predictions. We wouldn't be able to, decide this question experimentally. If you can't choose between these alternatives by going out into the world and letting that, having that determine which of these interpretations are correct, then that feels like metaphysics rather than physics. I think we need to find this other piece of the puzzle rather than fight amongst these different alternatives. All the matter in the universe obeys the laws of quantum mechanics. What sets apart from this is gravity, and gravity made manifest through space-time bending, and in particular actually clocks running at different speeds at different points in space. If I have a particle which is in a superposition of being in two places, then we don't quite know how that should bend space-time. And so there's this inconsistency. We haven't been able to resolve it, and that has been, in some sense, we're celebrating 100 years of quantum mechanics, but we're also celebrating 100 years of failing to quantize gravity. For a long time, people believed that it was impossible to combine these things, and it turns out you can. If you just assume, for example, that space-time itself, the speed at which clocks run, if you assume that we have to describe classically, then it turns out you can consistently have a theory in which matter is quantum, and the time it behaves more like a classical object than a quantum object. When does this transition between acting quantumly and acting classically happen? And it's maybe natural to think, well, maybe gravity plays a role because, well, it's when the object is very heavy that it starts to behave classically. And indeed, in this post-quantum theory, when objects become dense enough, then they behave classically. That's when they start to localize, because the way space-time bends around them, it forces those particles to localize. The belief is that quantum mechanics, in order to be consistent with gravity, will have to change in some way. And that is, in some sense, that's what happens in this post-quantum theory.
Where, at least my perspective, and I think the perspective of quite a large fraction of the community, may not agree with that of Jonathan Oppenheim, in that we do believe that to make sense of reality, to make sense of the quantum nature of all the other fundamental constituents of matter and fundamental forces, gravity itself has to be quantum in nature as well, because it interacts with everything else which is quantum. And so that means that if you take gravitational waves, and let's imagine you have gravitational waves which have been detected, they have been measured. If we were able to dim those gravitational waves as much as we could, we would see that they're just made out of finite, discrete levels of energy. And those levels of energy for gravitational waves of a particular frequency, we call those gravitons. And gravitons are the fundamental constituents of gravity, of gravitational waves, just like photons are the fundamental constituents of light, of electromagnetic waves. Now, in order to prove the quantum nature of gravity, or to prove that gravitons existed, we would need to just look at the effect of one graviton. But we can't. It's not only that we can't technologically, in fact, the effect of a single graviton would go beyond Heisenberg uncertainty principle. So we really are faced with a huge challenge there. We think, we know, and there's theories out there, not by me, but by many of my colleagues, that think that at the very beginning of the universe, there were quantum fluctuations of different constituents, of everything, in fact, including of gravity. So there were gravitons, like there is right now, but they were at the very beginning of the universe as well. And the beauty of them being there at the very beginning of the universe is that those get stretched to large observable values today, thanks to the evolution of the universe.
The main problem, in my view, with unifying quantum mechanics and general relativity is really that we still think of general relativity as a fully classical theory. So all the principles that underpin general relativity, we think of really as only being true in a definitive state, but not in this superposition way that quantum mechanics suggests. You start with the state of your system at a given time. You put all the information into this catalog, as Schrödinger called it, or a matrix, as Heisenberg called it. And then you evolve this in time. You use Schrödinger's equation and you say, how will this state change if I look at it, if I experiment with my system in 10 minutes time? What I'm advocating, and one of the possible approaches, is to really include time into that description. So rather than just giving the state of your system at a single given time, you give it not just for all the space, but you give it for different times as well. You include quantum mechanics into your temporal description. Even when you unify space and time in this way, it seems to us that they still behave differently. So we can, for instance, move in space in one direction. We can go from here to Manchester, and then we can just drive from Manchester backwards and on our return journey. Whereas in time, the question now becomes, if we go forward in time, does that really mean that we could equally well then go backwards in time? And that, I think, is a fascinating question, because I think in quantum mechanics, there is no unique time. Sounds like science fiction, actually, but it doesn't really contradict anything that we know in quantum mechanics. My hope, ultimately, is, of course, it gives us something new. Maybe this is a better way of phrasing quantum mechanics in order to try to merge it with general relativity.
If you increase the mass of the objects that you can place in a quantum superposition, you will at some point reach a level at which the effects that gravity can display are relevant and can be measurable. And this is the direction in which I kind of proposed an experiment recently, where you consider an object which is just above the threshold of the mass that can be currently superposed in current experiments. The idea is to put them into a quantum superposition. So in the experiment, you're trying to create a quantum correlation between these two masses, which is called entanglement, by using gravity as a channel that allows these two masses to interact with each other and to create these correlations. Now, the test says that if you can detect this entanglement, of course this is a big if in the sense that it's a challenging experiment, but if you can detect the entanglement and guarantee that nothing else did it, so it's really happened through gravity only, then gravity as a mediator of entanglement must be quantum itself. And the significance of it is that it would be, if you could detect entanglement by this means, you'd be refuting for the first time relativity as a classical theory of gravity.
In the near term, we have these experiments to determine the nature of space-time, whether it's quantum or classical. So that is coming, and that could either confirm the majority of scientists' belief, which is that space-time is quantum, or it could represent another paradigm shift. And then as well, we have quantum computers which are being built, and that is huge. That, it's probably before we have a fully functioning quantum computer, that'll probably be decades away. But that is exciting because, not only from a practical point of view, in the sense of we'll have this computer that we'll be able to use to compute all these things incredibly quickly, but also conceptually, the quantum computer is like a cat, which is dead and in a superposition of dead and alive. So the quantum computer itself is just a remarkable thing which is really quantum in nature, in a way, in a macroscopic system which is quantum in nature. I think that the coming decades are very exciting in terms of quantum technologies, understanding quantum mechanics, understanding how it might fit together with gravity. I think it's a pretty exciting time to be doing physics right now.
There is a very interesting set of possibilities ahead of us, both in merging quantum theory and general relativity together, that will open up inevitably many new doors. But also there are these very interesting domains that physics hasn't touched yet. Things like the physics of the mind and the physics of life. Many physicists have been wondering about these issues. Von Neumann was one of them. I think Wigner and Bohr and other people, Schrödinger of course, have been considering these problems. But from the point of view of physics, we haven't created a good picture of what, for example, the emergence of life is, how the emergence of life occurred. Of course, there are some good theories. The evolutionary theories are completely acceptable and satisfactory. But I think I'm talking about more predictive models where we can actually emulate these kind of phenomena in the lab and reproduce them. There are probably laws to be discovered, just like for thermodynamics, there was something to discover in the context of heat engines, which are macroscopic machines, and for computers with universal quantum computation.
It seems to me that the trend certainly is for quantum physics to leave the microscopic domain and to go into the bigger and more macro domains. So I think the first frontier properly is chemistry, maybe even rephrasing the basics of chemistry in terms of bonding, in terms of entanglement, will define the next decade or so. And then, of course, going from chemistry into biology. So it seems like quantum physics is leaving the microdomain, going towards biology, then possibly even asking questions in neuroscience and so on. More and more macroscopic seems to me to be the trend, which of course then brings a very interesting question for our perception. Why is it that we still see the world as more or less classical, really, in our own macroscopic domain? And I think this is something extremely interesting to investigate. And the question is there for me, which I think could be then interesting for all of us ultimately, is whether you could even technologically modify our own perception. I think that's going to be the next frontier in many ways, whether you could really somehow augment our way of interacting with reality to open it to this broader, wider sense of possibilities. As we test the theory in these completely novel domains, in complex chemistry, in biology, maybe in neuroscience, it is possible that we will discover that quantum mechanics is not enough. Equally, if you go from the other side, from already the biggest objects, we do have some evidence in astronomy, in cosmology, that there are problems that we don't know how to address. There is the dark energy, dark matter, the origin of the universe, Big Bang. All of this is wide open.
We do realize that if the vacuum is not empty, if it's filled with energy, then it should have an effect on the evolution of the universe. And understanding why the energy of the quantum vacuum doesn't lead to an accelerated expansion of the universe, which is not way, way, way larger as compared to what we observe, is one of the most embarrassing questions we have today. We are not just doing particle physics on one side and gravity on the other side and astronomy on the other side. We're really merging all of our understanding and using cosmology as a microscope for fundamental physics, using the infinitely large distances to probe the infinitely small and combining this with black holes. So we are very much at the interface with all of those fields and put them all together into one combined framework. Where are we going after we have 100 years of quantum mechanics? I think it's an excellent question. One thing we have to bear in mind is that we had Newton mechanics for a long, long time before anything else came along. So 100 years in the scale of human history is really not a long time at all. But one thing which is essential is the current framework we have already tells us that there are new things to uncover.
We call it interpretations, but I think most likely we're just missing some physical piece of the puzzle that we don't yet have. There's some physics that we don't understand. And I think once we have that, then we won't need to fight about interpretations because it will be much clearer what's happening.
We'll find at some point the successor of quantum theory. It won't be quantum theory. It will have gravity in it, and gravity will be quantum. That's how I imagine. Of course, I could be wrong, but I think that's what I expect. And this theory will still have effects like entanglement, quantum superposition, and quantum computing. It will have a lot more as well. So I expect the next theory to be even more counterintuitive than quantum theory is. And I hope that also by that time we'll have stopped thinking of quantum theory as weird and we'll have absorbed its consequences into our way of thinking.
We know already from the theoretical point of view that we need to better interrogate nature. Understanding how to even ask the questions we need to ask is becoming very, very challenging, and making the connection between those very formal, very abstract questions and then putting that back into context, into what it tells us for the nature of reality, what it tells us for what it is we see in the sky, what happens in experiment, is very, very challenging. But we are making progress, in fact. Whether the actual breakthrough is going to come next year or is going to come in 1,000 years, it's really hard to say at the moment.
And it's not just physicists. Artists too are reaching for the quantum world. The strange and fuzzy nature of reality at the quantum world is still confusing for most physicists. Where physics fails to explain some of these bizarre phenomena, art and creativity can step in, giving a new perspective. Both artists and physicists have a shared curiosity in trying to explain the world, how we perceive it, and what it might be made of. Here, we delve into how art might better explain the quantum universe.
The early stages of art and science are very similar. It's this first-person, intuitive aha moment that we're all after. However, the art helps us to get us closer to that moment again, to feel, to experience directly. We are here in the exhibition called Cosmic Titans, Art, Science and the Quantum Universe. We invited 9 artists to come and work here at the University of Nottingham in ongoing physics experiments.
By discussing and sharing common practice and how we develop our scientific experiments, but also artworks, there is a strong similarity. You start setting something up, building something, but then you have to ever so slightly change it and adapt it until it does exactly what you want.
There are multiple outcomes of that process. One of them are fantastic artworks, but also, of course, pushing forward science in the fields of quantum science and astrophysics. Konrad Shokras was our first artist in resident. He created the piece Ring Down, which is a big machine that deals with the last moments before 2 black holes collide.
And when 2 black holes in spiral and come closer, they form a new black hole. This newly formed black hole gives off what we call quasi-normal modes, some last bursts before the black hole settles in its new state. These modes is what we're trying to simulate in my lab, and we do this using giant quantum vortex flows. Konrad visited our labs to understand how we do science, to pick this up, and this is reflected in his artwork.
This is something that is not visible to us, it's intangible. And so in his audio-visual artwork, you can feel, see, and hear this event. It's a very noisy experience, but we give the audience member the agency to start it. So you press a button and then Ring Down starts.
For the first time, I really felt how violent these effects are by seeing these 2 gigantic bells representing the black holes swirling around and the noise they're making. You start to step inside your simulation and you appreciate the perspective that you have. The way they approach things is different. They have a lot of technical skills that opened up new ways of exploration also for us, which made the whole scientific approach much more playful. One direct example, with one of the artists, Alistair McClymont, together we're developing sensors for quantum vortices in quantum liquids. And these are extremely hard to see. At the moment we're developing techniques using lasers. And when Alistair came, he suggested that we should also explore techniques using white light, a torch, to visualize quantum vortices, which led us to look into old-style optics. And it turns out that, in principle, that you can go down this route. You don't need to always work with the most posh system. You can go back and approach the whole problem from a different angle. So it has already changed the way we are developing these sensors.
The process was really fascinating to observe because there was a back and forth, a ping-ponging between the artists and the scientists while they were developing the artwork and the science experiment. In the center of the artwork, you have a water dish that is excited by a speaker underneath that sweeps through frequencies. And the surface of the water creates these ripples that over time get more and more chaotic. A white light, it shines onto them, it gets reflected and magnified onto a screen. We also have a sub-bass speaker that makes these frequencies experiential in us. So the visitor that walks in can feel this moment where from a homogeneous background, structure and chaos appeared. This is sometimes uneasy, uncomfortable experience. However, this was really important for us to have an artistic connection between us as humans and our bodies, feeling a little bit what it must have been like in the very, very early universe. All of the artists were really fascinated by making the intangible tangible. And what I mean by this is that in science, we're dealing with phenomena that are too vast, too distant, too small for us to ever experience them directly. Whereas the artworks that we're showing here, they allow us to get closer to these concepts and ideas that otherwise we can never actually directly grasp. We gave Studio Above and Below a very challenging task to make experiential the quantum world and all of its unintuitive weirdnesses. They chose to use the Apple Vision Pro headset to have almost eye vision, so it feels incredibly real, to zoom into this subatomic particle world where things don't make sense anymore to our classical understanding. And then you experience how everything can happen at the same time, or how you, just like particles, tunnel through obstacles that otherwise, in a classical sense, you will never be able to go through. So it brings this weirdness into our human experience. The Blind Proliferation by Konrad Shawcross deals with the idea of the multiverse, that at the very beginning, not one universe, but many universes came into existence. In the center of the piece, there is a six-sided cage with lights going up and down really slowly, and they cast shadows on the wall. Left and right of this system, you have two identical scientists' offices. You see the methods, the tools that we have as people to understand the source of these shadows without ever actually being able to directly see them.